Hello, hi everyone. Today's topic is artificial intelligence in VLSI. So we are presenting it from Radiant Semiconductor. So Radiant Semiconductors was founded in 2018, and we have branches in Bangalore, Hyderabad, and USA. We have around 200 plus employees and 30 plus clients and 50 plus projects. So, to brief about me, so I'm Casey, having 19 plus years of experience in VLSI. Currently working as senior director at Radiant Semiconductors, taking care of end-to-end product development in both the digital domains and analog domains. Now, let's see what is artificial intelligence. Okay, so revolutionizing lives with artificial intelligence. Okay, so artificial intelligence is set to transform our world in profound ways. Okay, from autonomous cars and advancements in healthcare to enhancing image recognition on our smartphones. So this revolution touches everyone. Okay, in the realm of electronics, technologies like convolutional and recurrent neural networks, along with deep learning algorithms, are paving the way for a new silicon renaissance, driving innovations in chip design, software, and IP. Okay, as technology advances at an exponential rate, semiconductor design has grown increasingly complex. Right. However, AI is empowering design engineers to overcome these challenges with unprecedented results and efficiency. Okay, so this is a brief overview as how artificial intelligence is revolutionizing our lives. All right, now let's look at some of the key benefits of artificial intelligence in chip design. Automated insights. Okay, so by leveraging historical data, AI driven chip design technologies provide valuable insights that inform and enhance future designs. Okay, increased productivity. These tools significantly boost engineering productivity, enabling faster iterations and improvements. All right, and of course, faster time to market. Right, I mean entire chip development. Right, I mean schedule is the one part where we majorly look into along with PPA. Right, so that's where like faster time to market will come into picture. So with artificial intelligence, companies can expedite the development process, bringing products to market more quickly than ever before. Okay, so please join us as we harness the power of AI to revolutionize the semiconductor design and unlock new possibilities for the future. Right, accelerating the AI revolution. Okay, in a world defined by rapid technological evolution, artificial intelligence is the driving force transforming our daily lives. Okay, from smartphones to vehicles and even within our homes, AI is reshaping how we interact with technology, offering benefits that go beyond mere convenience. All right, so key highlights. What are the key highlights of artificial intelligence? Right, unlocking efficiency. AI is essential for achieving unparalleled efficiency and personalization in various applications. Architects of change. VLSI companies are not just bystanders, they are actively shaping a future where the potential of tomorrow's technologies is limitless. Alright, AI in action. From AI driven IC and SoC designs to AI powered verification, PCB design, and multi physics analysis, they are leveraging AI to pioneer a new era of on device AI IP and next generation chip creation. AI is embracing this transformative journey and is set to redefine the landscape of technology. Everywhere, I would say, from end to end, we are using artificial intelligence to help us achieve time to market, right? And of course, to improve the PPI as well, right? Now, navigating the complexity of advanced process nodes, right? I mean, as we push our limits towards advanced process nodes like 3 nanometer, 2 nanometer, 1.8 nanometer, right? So the complexity of the chip keeps increasing. How do we navigate the complexity, right, which are being posed by advanced process nodes, right? So as we push into advanced process nodes, the challenges of achieving optimal power, performance, and area PPA have intensified, right? It's not just about PPA as well, right? I mean, going forward, it is like PPAC, Yes, that is power, performance, area, congestion, and schedule. Right? So traditional manual methods are no longer viable, especially with the shrinking market windows that demand faster, better results. Right? So now what are the key challenges in artificial intelligence? Increased complexity. The intricacies of modern designs require more than just conventional approaches. Okay. Time consuming tuning. Right? Traditional methods often take months, involving hundreds of trials, and still may not yield optimal results. Okay, so these are some of the key challenges what we have as on date, right? And how AI can help us to provide the solutions, right? AI driven solutions. AI driven technology can revolutionize this process, enabling faster and more efficient optimization. By leveraging advanced algorithms, we can streamline design workflows, reduce tuning time, and achieve superior outcomes. Right? Embrace the future of chip design with AI and tackle the complexities of modern semiconductor challenges head on. Okay, so this is the advantage of having AI in order to deal with the complexities that are coming because of advanced process nodes. Okay, now let's see what are the key benefits of artificial intelligence in chip design, right? Optimizing power, performance, and area. So AI-driven electronic design automation tools excel at optimizing the PPA of chips. Okay, this ensures that the chip consume minimal power while maximizing performance and minimizing physical size. Okay, so the EDA tools are to be equipped with artificial intelligence, right? When we are implementing the design, right? Enhanced design exploration. AI technology can analyze existing human designs and rapidly explore various optimized placements. Okay, this capability allows for quicker identification of configurations that improve power consumption, performance, and space utilization. Okay, so whatever the implementation methodology that has been used by the user, right? So those implementation methodologies can be enhanced by using the artificial intelligence. That's where we call it as enhanced design exploration. Okay, the more and more we apply artificial intelligence, then using the machine learning concepts, the tool will be able to understand about the design. Okay, and then it will be able to provide the enhanced recipe for dealing with the PPA optimization of those designs. Okay, so faster design iterations. By leveraging AI algorithms, design teams can evaluate multiple design approaches in a fraction of the time it would take manually. This speed accelerates the design process and leads to quicker iterations. Okay, faster design iterations. Okay, because if we have to reduce the time to market window, then we need to come up with enhanced design exploration, which means we need to have a proper recipe which will help us to meet our PPA targets. Similarly, we need to reduce our design iterations. Okay, and then improved quality of results, right? I mean, we have to improve our QR. It can be related to power or it can be related to performance, timing, right? Any of the metrics what we have in order to close our chip, right? We have to improve the QR in the shortest time span possible, right? AI not only speeds up the design process but also enhances the quality of the final results. By pinpointing areas for power optimization and identifying potential issues early, AI contributes to more robust and efficient chip designs. Okay, so these are some areas where like we can significantly use artificial intelligence in chip design. Next, automation of place and route. AI can streamline the place and route process for integrated circuits, generating more optimal layouts. This reduces the time and effort typically required for these complex tasks, right? Now, for place and route, which is like major chunk of the schedule, right? Automation of place and route can be done using artificial intelligence, okay, where it can help us to reduce the time and effort, right? At the same time, it will provide us the optimal layouts without wastage in the silicon area, right? Knowledge-based optimization. Historically, optimal place and route decisions relied heavily on the accumulated knowledge of individual engineers over numerous projects, right? This method is not only labor intensive but can also become a bottleneck as design complexity continues to rise, right? So knowledge based optimization is another area where we can extensively use artificial intelligence. Okay. Similarly, intelligent scenario exploration. With AI, design engineers can instruct algorithms to explore various place and route scenarios using different parameters. This capability allows for a more efficient exploration of possibilities, ultimately leading to identification of the best layout options. Okay, so intelligent scenario exploration, right? Out of so many scenarios, which scenario will best work for us? Which scenario will best work for our product? Right? Which scenario will best balance out the PPA, right? So all these things, right? So they will help us out in speeding up the productivity. Okay, intelligent scenario exploration, right? Enhanced design efficiency. By automating these processes, AI significantly reduces the manual workload for engineers, allowing them to focus on higher level design challenges. This increased efficiency accelerates the overall design cycle and improves productivity. Okay, enhanced design efficiency. All right. Now let's look at a couple more examples as where we can use artificial intelligence in chip design. Automating complex tasks, right? AI tools can automate many aspects of chip design, right? That traditionally relied on extensive prior knowledge and experience. Okay, this needed architects, this needed experienced people to be present, right? Now it can be handled by artificial intelligent tools, right? EDA tools, right? So this automation allows less experienced engineers to contribute effectively to complex projects, right? So this is nothing but automating complex tasks, right? Which will help us again to minimize the number of errors, right? To have a thorough understanding of the issues, foresee the issues, and then to tackle the complex task easily, right? Now, enhancing skill development. By leveraging AI, organizations can provide valuable insights and support to new engineers, enabling them to learn and adapt more quickly to the demands of the industry. Okay, fostering innovation. With AI handling routine and complex tasks, skilled engineers can focus on higher level design challenges, driving innovation and improving overall design quality. Right? They can work towards innovation while the AI takes care of the regular routine task. Right? So we can do delegation of the activities as well using artificial intelligence. Okay, meeting industry demand. AI helps companies efficiently utilize their existing talent pool while simultaneously addressing the skill gaps, ensuring that the growing demand for semiconductor chips is met without compromising quality. That's the most important thing, right? I mean, we don't want to compromise on our quality, right? So whatever the industry demand is there, we need to meet it, right? And to achieve that goal, artificial intelligence will help us efficiently. Okay, enhanced decision making. Okay, AI analytics can process vast amounts of data to identify trends, optimize designs, and inform decision making. This is especially useful for the project leads, right? In order to do the decision for the projects, right? Empowering teams to work more effectively, right? So this will impact your entire product cycle if we know how to use artificial intelligence to identify trends with respect to different data what we have in the program. Okay, automated insights, right? By automating the analysis of design data, AI can provide actionable insights that help engineers tackle complex problems with greater precision and speed, right? And then similarly, addressing skill gaps. AI tools can compensate for the shortage of experienced engineers, right? By enabling less experienced team members to navigate complex tasks, thus broadening the talent pool, right? So we can even address the resource gap as well by using the artificial intelligence. Okay, driving innovation. With AI handling data intensive tasks, engineers can focus on creative problem solving and innovation, leading to breakthrough in chip designs. Okay, now how does AI work actually in chip design? Right, how we can integrate artificial intelligence into chip design. Okay, so one of the groundbreaking AI technologies used in chip design is reinforcement learning. Okay, this is one of the groundbreaking techniques what we have in order to use artificial intelligence into chip design. Okay, this powerful approach, which is nothing but reinforcement learning, right, this helps optimize chip configurations to achieve the best possible power, performance, and area PPA outcomes. Okay, key features of reinforcement learning in chip design. Okay, one, utilization of multiple floor plan designs. Okay, reinforcement learning analyzes various chip floor plans to identify the optimal configuration that enhances PPA. Okay, normally when we do physical design, so we have to go through churn of identifying the best floor plan for our block or subsystem or chip level, right? But then all these iterations can be reduced by using artificial intelligence based reinforcement learning, right? So the reinforcement learning will analyze our design and it will try to come up with a optimal floor plan which best utilizes the available die area in order to meet the PPA requirement, right? Now, parameter driven optimization. Electronic designers input specific parameters into reinforcement learning system. If at all the user is having specific parameters that need to be met for his design, right? I mean, we have the provision to give them as input to the reinforcement learning engine, right? Where these parameters guide the artificial intelligence in optimizing. So the artificial intelligence will focus more on these specific parameters given by the user, right? Okay, so parameter driven optimization and how it will help us to reduce different metrics in the program. For example, wire length reduction is one such metric. Okay, so minimizing wire length to enhance performance and reduce power loss, right? So if we come up with a floor plan where wire length is reduced, which means in the total path delay we are reducing the net delay, which will automatically help us to improve the performance and it will also help us to close the timing faster, right? Similarly, as the net delays come down, right, it will also help us to minimize the power consumption because the number of cells getting added to meet the DRVs of the wire, they come down drastically, which will again help us to minimize the area and power consumption. Similarly, derate application will come down because of wire length reduction. Similarly, signal integrity effects also will come down because of wire length reduction, right? So many things are interlinked if we focus on this particular parameter, that is wire length optimization. Okay, now congestion and density management. Okay, density is related to cells, congestion is related to nets, right? So congestion and density management, managing chip density to avoid hotspots and ensure efficient layout. Okay, so we can also take help of artificial intelligence to take care of global congestion, to take care of local congestion, to take care of cell density, so that it will help in managing the overall chip density, right, to avoid any kind of hotspots, right, and to get the efficient layout, right? Now, power consumption minimization, reducing power usage without sacrificing performance, right? So we are trying to reduce the power. It can be leakage power or it can be dynamic power, right? Again, in dynamic power, we have short circuit power and then switching power, right? So any kind of power reduction leading to the total power reduction, right? Artificial intelligence will try to reduce the power as much as possible without compromising on the performance. The best example is wherever we have setup margins, we are replacing the VT flavor in the data path, right? So that we can reduce on the leakage power consumption. Thereby the overall power consumption can come down. right? Similarly, area optimization, right? Making the most efficient use of the available chip area with minimal white spaces. Okay. So many advantages are there once we know how to use artificial intelligence in chip design work. All right. Now, what is another most important advantage? Continuous improvement, right? I mean, that is the advantage of RL system what we have, right? As the RL system receives feedback from its design outputs, it continuously refines its algorithms, learning from previous iterations. This enables it to produce better designs autonomously over time. The more and more data you provide to RL system will analyze how our design is performing, how our design is behaving, right? And in order to achieve the targeted PPA goals, right, the RL system will evolve, keep evolving, right? And based on the design, it will come up with a recipe which will help artificial intelligence to provide better and better results. Okay, the more space we provide for RL system to play with, right, it will help the artificial intelligence to achieve the needed PPA targets better, right? That's how it is, right? Continuous improvement. So by harnessing the power of reinforcement learning, AI is revolutionizing chip design, allowing for faster, more efficient and higher quality outcomes. Okay. Now, let's look at harnessing AI for predictive insights in chip design. What do we mean by predictive chip design? Predictive insights. Getting to know the problems ahead of time. That is predictive insights. Okay. AI models powered by fragmented data points from the electronic design automation compilation are transforming the chip design process. Right? By analyzing these data points, AI can predict potential bottlenecks, performance constraints, and power inefficiencies before they disrupt the workflow. Okay, so we can beforehand come to know what are all the potential bottlenecks are there in our design, what are all the performance constraint issues are there, what are all the power inefficiencies that are there in our workflow, right? And how does the artificial intelligence come to know about it? Based on multiple data points that it is getting from the EDA tools, right? Which is practically difficult for the user to analyze and come up with this bottleneck analysis, right? But however, now with advancement of technology, especially the RL system, right, we are able to analyze trillions together of data that is coming from the EDA tools in order to foresee the problems in our workflow and help the user to come up with the proper workflow that can mitigate these problems, right? We are doing the damage control here using the artificial intelligence. Okay, so key benefits of AI predictive capabilities. Okay, proactive problem solving. With foresight into potential issues, engineers can address concerns early in the design process, preventing costly delays and rework. Right? This is one of the critical and most important thing what we need today in the industry. Right? Considering the mounting cost of semiconductor fabrication. Right? Informed decision makings, right? Informed design decisions, right? The insights provided by artificial intelligence empower engineers to make data driven decisions, right? Sometimes we have to decide whether we can go with certain design margins, can we go with certain clock frequency, can we go with certain set of constraints, can we go with certain set of power targets, right? Signal integrity targets, right? Now, while doing those decisions, it is always suggestible to have data driven decisions being made, and to have the data driven decisions, artificial intelligence will help us out. Okay, enhancing the overall quality of the design. All right, fostering an efficient design culture, right? This anticipatory approach promotes a culture of efficiency and innovation, allowing teams to focus on creative solutions rather than reactive problem solving. instead of waiting for the problem to come and then start addressing the problem, right, which we call it as reactive problem solving. It is always good that we go with creative solutions, where we foresee the problem and come up with solutions beforehand, right, instead of waiting till the problem comes and then searching for the solution, right. This is nothing but fostering an efficient design culture. Okay, by integrating artificial intelligence into the design workflow, we can create a more streamlined, effective and forward thinking chip design process, right. Going forward, we need to have artificial intelligence which will help us to come up with forward thinking chip design process, where we can foresee the problems, right, and accordingly do the chip design process. Okay, now reimagining engineering team efficiency in semiconductor design. Okay, one of the most significant challenges in the semiconductor industry is aligning designer resources with the exponential growth in the chip demand. Okay, as designs evolve into complex system on chips featuring numerous hierarchical blocks, they generate vast amounts of data throughout the iterative development cycle. When harnessed effectively, this data holds untapped potentials to significantly elevate the efficiency of engineering teams. Okay. Now, what are the key strategies related to enhancing efficiency? First is systematic data review. Consolidating data review into structured knowledge-driven process facilitates accelerated design closure. This ensures that all team members have access to critical insights, reducing bottlenecks and enhancing collaboration. Okay, next is seamless knowledge transfer. Okay, implementing a refined approach to data management. Data management is again a vast subject which we have to take up, okay, in the chip implementation process. Implementing a refined approach to data management enables seamless knowledge transfer between projects, from project A0 to project B0 to project C0. Everywhere data management comes into picture. This not only speeds up the onboarding process for new team members, but also enhances continuity and innovation. This is very much true when we are transitioning from one project to the next project, which is again the revision of the previous project. Okay, and this will help us a lot when we are onboarding new team members, right? Instead of again ramping them up, if we have a proper data management setup done, then this will help us to have a seamless onboarding process, and the project work can be continued without any interruption. Okay, now boosting productivity, right, this is another advantage what we have. By optimizing how data is utilized, engineering teams can significantly improve productivity without the need to exponentially expand team sizes. Okay, so we can rely on artificial intelligence, right, and the need for exponentially expanding the team size, right, this can be reduced. Okay, on top of it, along with reducing the exponential team size, we can also boost up our productivity. This is critical for the semiconductor industry to meet the increased chip demand efficiently. Okay, reimagining engineering team efficiency through effective data management and collaboration is key to driving innovation and ensuring success in a rapidly evolving market. Okay, so boosting productivity is one more important thing. Now let's look at ensuring systemic AI integration into semiconductor ecosystem. Okay, to fully utilize the potential of AI in the semiconductor industry, a systemic integration across the entire ecosystem is essential. This integration encompasses data collection and storage, effective systems for gathering and storing diverse data types are critical to support AI initiatives. Okay, tailored AI model development. AI models must be specifically developed and fine-tuned to meet the unique needs of the semiconductor industry, ensuring they align with the design peculiarities. Okay, each design is different. We have to align our AI as per the design requirement. Okay, robust AI infrastructure, that is again very important thing. Okay, a solid infrastructure capable of managing various data formats is the cornerstone of successful integration. We need to make sure that we have that infrastructure to utilize AI to the maximum potential. Okay, this ensures that AI models can operate effectively and deliver valuable insights. So many things go in place, not just having AI in place. Okay, we need to have proper infrastructure, we need to have proper model to be developed, right? We need to have data collection and storage as well before we start applying AI in the semiconductor ecosystem. Okay, now another important thing is actionable insights. Okay, what are actionable insights? By aligning AI capabilities with industry requirements, we can ensure that the insights generated are accurate and actionable, driving efficiency and innovation. By prioritizing systemic AI integration, we can unlock new levels of performance and productivity in semiconductor design. So actionable insights is one more requirement what we need to have in order to get the artificial intelligence into the semiconductor ecosystem. Okay. Now, cultivating AI competencies within engineering teams, right? As AI becomes increasingly central to the semiconductor industry, the need for AI competencies within engineering teams is more vital than ever. Okay, upskilling the workforce to effectively leverage AI tools and platforms is a critical step towards creating a harmonized AI ecosystem. Even the engineer should be familiar on applications of AI before this can be integrated into semiconductor ecosystem. Okay. Now, what are the key steps in the journey towards proficiency? One, familiarization with the AI concepts. Providing training and resources to help team members understand fundamental AI concepts and technologies lays the groundwork for successful integration. Right? The engineer should be familiar with AI concepts. Collaborative approach. Encouraging collaboration between domain experts and AI specialists fosters a culture of innovation, blending deep industry knowledge with AI acumen. Okay, hands-on experience. This is most important. Offering opportunities for hands-on experience with AI tools allows engineers to develop practical skills, enhancing their ability to implement AI solutions effectively. Okay, so all these things go in place in order to cultivate AI competencies within engineering teams. Okay, now the last point is unlocking innovation. Engineering teams that are proficient in harnessing AI can unlock its full potential, positioning themselves as pioneers of innovation in the semiconductor landscape. Okay, so innovation is one more thing which we have to keep investing. Okay, by investing in AI competencies, we empower our engineering teams to thrive in an increasingly complex environment, driving the future of semiconductor design. Okay, now let's dive a little deeper into EDA tools implementation using AI. Right now, as we can see in this slide, due to traditional waterfall approach used for semiconductor designs, the development costs skyrocket and processes are iterative with increased TAT leading to delay in TTM. Okay, right now, as the costs are skyrocketing, schedule is the most important thing. Right, we need to bring down the schedule so that we can reduce on the TTA and as well as TTM. Okay, now if we look at the traditional waterfall semiconductor design, right, so normally from the applications to the transactions, functions, gates, circuits, and finally layouts. Okay, lot of iterations will go on between each phase of the program, right, the traditional waterfall semiconductor design. But when the advancement of AI is available, when we leverage AI as an assistant in EDA tools, can rapidly explore and learn about new designs and architectures to determine the optimal strategy for implementation, verification, and testing. Okay, this can significantly reduce the development costs, TAT, and reduce the compute cost by enabling more intelligent runs of EDA tools. Okay, rather than relying on a trial and error approach and indiscriminately simulating all kinds of circuits, targeted AI enabled runs can be used to achieve similar results. We are reducing on the iterations. Okay, in the end, compute cost also will decrease. We don't have to invest a lot on the infrastructure as well if we effectively use artificial intelligence to reduce the number of iterations. Okay. Now let's see the EDA data. Okay, EDA data is very complex and unstructured. Okay, so when you look at the data storage, right, it can be machine learning models, verification, layout shapes, and then again log files, analysis reports, run scripts, input files, right? So many things are present in the data storage, right? And these are all the disks where the data storage is maintained. Okay, now using artificial intelligence, right, the RL system which we spoke about, this RL system will analyze the data that is present in the stored disk, right, and then it will come up with the best recipe for meeting our PPA in the layout. Okay, that's the advantage, which is practically difficult for the user to achieve. Okay, delivering better, faster, cheaper semiconductors, okay, with DSO.ai, right? I mean, this is one of the advanced tool what Synopsys has released in 2020 with the launch of Synopsys DSO.ai in early 20. Similarly, from Cadence we have Cerebrus, which was launched in 2021, right? We entered a new era of breakthrough chip design. This industry first autonomous AI application for chip design transforms how we optimize semiconductors, enabling us to deliver superior results more efficiently. Okay, what are all the key features, right? Optimization at scale. DSO.ai utilizes reinforcement learning, the same RL system, to explore vast design solution spaces, enhancing power, performance, and area. Higher productivity. By automating less consequential decisions, DSO.ai alongside Synopsys Fusion Compiler and IC Compiler 2, which are all again the physical design tools, right, significantly boosts engineering productivity and delivers results faster than ever. Okay, if we utilize DSO.ai along with our regular physical design tools, which are Fusion Compiler, we also call it as a single graph tool because it can do both synthesis and as well as PNR, and then IC Compiler 2, which is our again regular standard physical design tool from Synopsys, right? Along with the regular EDA tools, if we also have AI capability, right, attached to it, then it will significantly boost engineering productivity and deliver results faster than expected. Okay, then multi-die design optimization, right, as we are talking about 2.5D IC, 3D IC, chiplets, right? So for complex designs, Synopsys 3D SO.ai integrates fast native analysis engines, ensuring optimal thermal integrity, signal integrity, and power network design. Experience the future of chip design with DSO.ai, where innovation meets efficiency, right? Now, how to unlock the power of autonomous RTL to GDS to full flow optimization, right? With Synopsys DSO.ai, the optimization process is fully automated, transforming the chip design landscape. This innovative approach significantly reduces design time, enhances design quality, and maximizes PPA, right, potential across both logical and physical domains. What are the key benefits? High performance. Achieve superior chip performance with streamlined processes. Lower power consumption. Optimize power usage while maintaining efficiency, right? Smaller chip area. Design more compact chips with less manual effort, right? By leveraging autonomous RTL to GDS to full flow optimization, designers can improve the efficiency and effectiveness of the chip design process, allowing for faster time to market and more innovation solutions, right? Experience the future of chip design with Synopsys AI, right? So this is one of the advanced tools from Synopsys. Okay, now introducing breakthrough AI engines, right, through Synopsys DSO.ai. Okay, one of the standout features of Synopsys DSO.ai is its groundbreaking RL engine, reinforcement learning engine. Right, this innovative technology intelligently learns during the optimization process, allowing it to be effectively narrow down the design space. Okay, what are the key advantages? Efficient optimization, capable of optimizing trillions of design recipes leading to superior results. Okay, faster time to results. accelerates the design process, getting you to market quicker, reduced compute costs, okay, lowers expenses associated with the design space optimization. Okay, with the DSO.ai, experience a transformative approach to chip design that harnesses the power of AI to deliver exceptional outcomes. Okay, now with Synopsys DSO.ai, designers can simultaneously optimize for multiple objectives, including performance, power, area. This integrated approach allows for the best possible trade-offs, leading to more efficient and effective designs. Key benefits: comprehensive trade-offs. Achieve the ideal balance between competing design objectives, rapid exploration. Quickly explore a wide range of design options to find the best fit for your specific needs, saving valuable time and resources. Enhanced 3D design optimization. Synopsys 3D SO.ai utilizes AI to optimize the thermal, power, and signal integrity across expansive 2.5D and 3D design spaces. Transform your design process with DSO.ai and unlock new levels of efficiency and performance. Okay. Now, let's look at some of the key benefits. Okay. Unbeatable PPA results. Okay. Every project, every time, explore a larger scale of choices in chip design workflows. You will have multiple recipes to play with. Unbeatable PPA results. Fastest time to design, right? Autonomously coverage to tape out ready solutions. Tape out ready solutions, which is very much important for BTO and MTO. Okay. AI grade productivity enable design teams to scale and operate at expert levels. Okay. These are some of the key benefits. Now, what are the other key benefits? Unprecedented efficiency. Whether it's reducing PPA, optimizing cost, exploring molecular design, or enhancing data analytics, right? AI powers you to achieve more with less. Similarly, revolutionized design, accelerating electronic system and molecular simulations to create innovative solutions with unprecedented speed and efficiency. Okay, we can use artificial intelligence even for molecular simulations also, right? Continuous innovation. LLMs facilitate data-driven insights, predictive analytics, and next-level abstraction, empowering you to stay ahead. Okay, smarter development. AI-powered tools continuously enhance their intelligence and responsiveness to your design. They keep learning it, right? Now, a brief on analog side as well, right? On how artificial intelligence is helping to improve the design cycle, right? Analog circuit design simulations were traditionally based on Monte Carlo approach. However, these approaches don't scale well. The number of samples required for a sufficient solution space coverage scales exponentially with design complexity. Okay, an AI-based approach represents an even more focused, intelligently directed way to navigate a large and complex solution space to find sample points that meet the specification. Okay, an AI capability can be devised as a sample-based optimization system that dynamically learns about the problem it's tasked to solve. Okay, AI approach can use actual multi-corner, multi-test bench simulations to drive exploration of complex corner and test bench dependencies. Okay, it can dynamically navigate process corners to reduce the number of simulations required while converging across all corners. The simulation time will come down in the analog circuit design by using the artificial intelligence, right? Through this process, the AI tool learns from its simulation experiments using a live feedback loop to converge towards a solution that meets the specification. AI system makes informed decisions based on the experiments that it runs. Okay, reinforcing its internal perspective of the problem and objectives, which enables faster convergence. This is one of the biggest advantage to reduce the turnaround time. Okay, now let's look at the analog layout part. Okay, PDKs don't provide the specific variants. Example, layout only cells, that is tab cells, decaps, fillers, and guard rings. Also, layout designers often create custom structure around PDK P cell. Example, creating customized routes for easy connections or extended power or ground mesh, right, that can be used per instance. All of these customized layout structures take time to build and often not reusable without extra effort. Okay, the principle behind P cells can be extended to generate common analog building blocks for the same benefits of efficiency, uniformity, and ease of maintenance. Some of the user-defined devices, which we call it as UDD, can be generated, which are shown to the right for accelerating analog layout. These are some of the common UDDs: power mesh, standard cells, custom tab, fillers, decap cells, mass with guard ring. Okay. So with this, we come to the end of the first part of artificial intelligence in VLSI presentation, and we'll be catching up on the part B next week, same time at 10 o'clock, 10 a.m. Okay, and if you have any questions, please feel free to drop it in the comments section, and we'll be happy to check those comments and then get back to you as soon as possible with the replies. Okay, thank you all for attending this wonderful session on the artificial intelligence in VLSI, and see you all soon in the second part of this session, which will be closure for this presentation as well. Okay, thank you all, thank you so much. Yeah, thank you.